Cool. I guess we'll just start. So how can I make this? Yeah, hide that. Cool. Today's gonna be a short sessions in terms of the content. I don't have much to go through because I actually want to go through a whole coding sessions, and through the coding session, I hope that could help you guys learn about that. And yeah, as you can see, today's topic is transfer learning. Just wondering, does any of you have already learned what is transfer learning, or you guys are just come here to you already know? Okay, yeah, a little bit. Okay, which is cool because then I can ask questions in the class, and you'll be able to answer it. No, I'm just kidding. I'm just kidding. I'm just kidding. Okay, so regarding transfer learning, so first let's go through today's agenda. Just not much. We'll start coding almost immediately after the next slide. And let's learn a little bit about transfer learning. Before that, I just wondering, has anybody has completed learning about CNN? Like, is anybody does not know anything about convolutional neural network? Or is everyone on track? Cool, seems like everyone is on track. So I can actually get directly into it without going through again the architectures. And so the first point is that when you're using the transfer learning, essentially the concept of transfer learning is that you're standing on the giant's shoulder. Essentially, you're using the already trained weight as you use the already trained weight as a starting point for your own algorithm. And as we all know, the training for neural network, sometimes we're just starting from scratch. We usually just generate a bunch of random number and we start from the random number. But here, transfer learning means that you use the already trained network. For example, like I don't know, VGG 16, inception block, all of that could work, and use that as a starting point for your network. Of course, make sure the layer configuration kind of match each other, and use that as a starting point to train your own task. So for example, if you're trying to classify cat and dog, then maybe an algorithm that help you classify I don't know, fox and tiger could work. I don't know, but like because the similarity of the weights, they kind of transfer to each other, but not really. That's why after you use the pre-trained weight as a good starting point, you need to freeze them, and add a new layer to the freeze weight. So why you freeze the weights is because when you're training the neural network, as you all know, during the back propagation sessions, they're actually updating the weight. But we're using the pre-trained weight as a starting point, and we don't want to ruin that by the first couple, bad run. So we freeze them at first, and then try our best to train the later added layers. And that's why after we add the new layers, when we back propagate, only the new layers we update, and the freeze weight will essentially stay the same. And the next step is, of course, you train the new layer, and the last step is that you unfreeze the pre-trained weight, because although that you're using it as a starting point, there's still some characteristic. For example, maybe you're using classification algorithm that trying to classify different sort of transportation tools like planes, trains, and stuff. And now you're only trying to classify between train and a car, for example. Then some of the weights in the original layers may be extra, or maybe even behaving against your new layers. So now you're trying to unfreeze them and fine tune the previous parameter. And usually you will see increase in accuracy as well as a decrease in the loss as well. So that's basically what is transfer learning in very, very short form because I just want to go to the coding sessions and to show you how that can be done with Keras. You can also done really easily with PyTorch. If you have any questions, you can ask me regarding PyTorch as well. But today we're using Keras because it's just short and simple. Okay, cool. That being said, we only have like four slides today, which is good. And maybe just let me start a collab. Start a new Google collab. If you guys want to code along with me, or if you guys want to train your own algorithm, you could also open a collab. You just type in, like everyone has Google, right? Typing Google collab, and you will get essentially this. You go here, and you can just say new notebook. They have a live coding sessions with an accessible GPU, so which is pretty good. Anyway, I will just leave this and start coding here. I'll just do a transfer learning study group 0EP5. Cool. And of course, the first step is that just make sure everyone is following. Does anyone are lost in the opening collab part? Use good. Okay, perfect. We'll start. Feel free to break me off at any point because sometimes I know the code doesn't make sense and you want more explanation of it. Just feel free to ask questions at any point and I'll just stop and help you guys out. Okay, so first we import NumPy, which is, we're dealing with matrix as always because we're in the, like when we're back propagate or front forecasting, it's just ax plus b. And since we have a lot of weights and we sometimes passing data in a batch, so that means that we might want to use matrix multiplication, which means that we're going to use NumPy. And also a tensor essentially is a matrix as well. So sometimes we might want to use NumPy to deal with that as well. But usually we use the other library. So we'll import Keras. Okay. So this is our import. Just make sure I don't have anything typed wrong. Hopefully this should work. That's it. Yeah, it does. Takes about 4 seconds. Okay. So first, I just want you guys to get a little bit familiar with Keras and how do you, like freeze the weight and stuff. So I'm just gonna use this quite a few simple examples to help you guys know how to build dense layer in Keras and kind of just visualize that for you guys. So we'll start a new simple layers like Keras layers.dense. Okay, and we have 3 units. That means that we have 3 hidden units in the actually not hidden unit, just 3 kind of just node neural network node in this layers. And we'll do layer build. No, actually, I think I need to passing the expected outputs size. Yes. And here I'm just building this layer with its expected output configurations. So I'm just I'll just print layer and let's see if this printed layer makes sense. Okay. Yeah, don't do that. Sorry, weights. I just print layer weight so that we can actually see what is exactly the starting weight that we're using for this dense layers. So as I just declared that it has 3 units, that means that each so the output configuration is expected that it's going to feed it to 4 kind of so the expected output is 4 to 3. is because it has 3 units, but I'm going to feed it to 4 upcoming nodes. So if I'm gonna draw it, it's gonna be looking something like, so you have 3, this is your dense layer, and you have 1, 2, 3. Sorry, I'm using my touchpad. It's not really good drawing. So 1, 2, 3, 4. It's looking something like this. So it's going to pass like this. 1, 2, 3, 4, and so on for the other node. And that's quite ugly, but clear it up. Sorry? Oh, okay. I'll just yeah, sure, I can do that. Can I do it? Control. Does that work? Cool. Okay. Yeah. Okay. So the value in the parameter essentially doesn't matter in this case because we haven't started training. So these are just some random starting point. But that's actually why sometimes you want to use transfer learning, because that gives you a good weight, and then you can just attach things to this beginning point, and then things will turn out good, because transfer learning, it usually trains really fast. And these doesn't really matter. As you can see, the bias term right now is 0, and not much to learn about. But in this case, I just want to print one more thing, which is trainable parameters. So here we're just starting a normal dense layer. That means that we haven't freeze anything. So sorry, before that, so let me just print number of parameters. And to do that, I'll just do list of layer, yeah, layer dot weights. So that gave me my total number of parameter, and this will be trainable weights. And you can, as you can see, this and this essentially will be the same. If I run it, yeah, it's going to be the same. So the next point is that I'm going to show you what is happening after we freeze something. So we'll just use the same example here, but I'll just copy and paste it down such that you have multiple references. And the next one is I'm gonna do layer trainable. Yeah, this is a Boolean variable, and I'm going to turn it to false. And that means that I'm turning this whole layer to be not trainable. This means that if I put it into fit or something, these type of weights, this specific layer will not get updates. So if I do this, so you can see now this number is turned to 0, and the whole layer freeze, which is what we want to see. And without further ado, let us just I know I'm using a handout, but I think some of the handouts are just kind of extra and not, I don't think the example they gave is quite helping us to learn the example here. So I think I would just directly dive in the actual transfer learning example, and then we'll just go through the models. And if you guys want to learn about exception, I can also go through that. But I don't think it's quite necessary because it's not traditional CNN layer. I can go through what is an exception, but exception is it's related to, I think it's separable layers, and that's kind of more complicated, a little bit more complicated in terms of visualize for compared to the traditional CNN layers. Anyway, let's just dive in. It has an inner model.
I have a question.
Yes.
So, 2 questions actually. The first one was the number 4. Is that the logits for the network?
That is not the logics for the network. You're just building a layer, so that is just the number of nodes in that specific layer. So if I undo this,
Okay, it takes the input is 3 and the nodes are 4.
yes, it's because it had 3 columns and it has 4 rows, and that's
Okay.
yeah. So this is
Um,
number. Sorry, I'm. And this is the shape. And this is none because it's flexible, so it's connecting whatever. So in this case, it's 3. It's putting 3 in none and 3 and 4 here. Yeah.
Okay. Secondly, when you do layers dot trainable weights, why does it say 2? I mean, layers dot weights, why does it say 2? Is that the different types of parameters, or is it like the only 2 parameters that you can train in the network?
It's the only 2 parameter. It doesn't really matter to the configurations, because if I change this to 5 and it's still printed, I think it will still print 2. Yeah.
Okay,
Yeah,
that's
it will
interesting.
still print. This number is not related to the configurations of what's happening with your weight, but it's just kind of, I just kind of use it as an indication of letting you guys to see how many percentage of the parameter are trainable and how you can turn it off. So don't stress about that too much. I think this this matrix is the direct indication of what's happening inside of the network, instead of, you know, like this simple 2, which is this is just using for you guys to see that some of the parameter is trainable, some of them are not, and seeing that after I turn it off, this becomes a 0. So I'm just using these 2 examples.
Right. Thank you so much.
Yeah, here is how you can turn the whole, so actually freeze the whole layer. Yeah. So these 2 examples are here to show you how to freeze this layer. Yeah, no worry. And the next one, we're just gonna, I don't know, let's see, starting the actual example. So in a model is here as sequential. So if you're using PyTorch and stuff, you guys are actually gonna declare your own class and kind of change things after you inherit it from the normal, you know, like the PyTorch classes. But because Keras enables easy, I guess, deep learning for the beginners, so sometimes, so you don't have to declare a own class for yourself. You can just use the sequential functions. So use this, consider is this as it's creating a list. And after you put layers in, I'll show you right in a little bit, like this. So you have a list, so you declare an input shape equals 2. Layers dense. So you're creating a dense layer here. 3 activation. We're using ReLU in this case. Whoops. Keras. Layers. And we'll add another dense layer here. 3 activation equals to ReLU. Okay. So we're using did I forget somewhere? Yeah. Yeah. So we're actually, for the sequential, we're passing a list of neural network layers that were created with Keras. And this sequential functions, essentially, after you put in the list of the layers, the sequential functions is going to help you to connect first layer, second layer, and the third layer together. And now you have a model. instead of you having to go in and declare your own one. If you're guys are curious, I can show you an example of how you exactly do it in the PyTorch, because that's the more, I guess, actual way of doing it. And this is just simple model that's embedded into the Keras library, but this is indeed really easy and really time saving. So actually easy to debug as well. So here is sequential. So now I'm actually connecting another model right here using the thing that we have built previously. So now we have Keras dot inputs, and we're gonna do shape equals to 3, exactly the same as previous one. Next one is row. Okay. So in our model, which is the model that I just declared here. So this is the inner model, and I'm kind of just making a sandwich here. So the previous one is the inner model, and the sorry. So this is kind of like the you know, when you're eating a sandwich, this kind of like the meat and vegetable here, and I'm putting the top bread, which is the input, and another bottom bread, which is like Keras layers. I'm adding another dense layer. 3 information signal. Cool. And this means that this is parameter that's outside, and I will show you in a little bit, because you know what else I can do? I could just substitute these two in here. I'll just substitute this line with the previous, these two lines, and it will result in the same model. But can somebody maybe guess why I'm putting the inner model off? In terms of the freezing, like I can give you a little hint, is that I put it out because I want to kind of freeze something. So does anybody want to take a guess that how would this enable us to kind of freeze parameter and help with the transfer rate? No one want to take a guess? Sorry? Yeah, the maybe, but the exact reason is that, oh wait, somebody is typing the chat. Can we get a hint? Yes, you can get a hint. Actually, I'll just tell you the answer because I got much more questions later. So you got, I'll just give this one to you. So if I gotta, so for example, in this case, I'll do this print visualize for you guys. If I do print model, and that will not show me. So let's do model layers. Does that shows me things? Oh, it doesn't shows me things. Let's do model layer 0. Oh, it doesn't shows me things. Wait. Okay, so this is your. Or I can do, essentially, I can do trainable. So you can see that right now, if I do layers 1, actually before that, let me just do 2 layers. We have this layer and this layer. And if I do before this over here, if I add more lines, so if I do model trainable equals to false, that means that I'm freezing this whole model. That means that every single weight is going to be freeze by me. And then if I print, where's 0. It's going to be false as well. But if I change it to 1, it will also be false. But what if I only turn the inner model? Now you see that only the inner model is turned off. That means that we don't have to freeze our entire layers, because in Keras, if we do sequential and we add every single layers into here, and we basically cannot selectively turn off some of the layers that we wanted to freeze. That means that in the transfer learning, we can really basically choose the layers that we want to free and choose the layer that we want to, train. So here, I'm just saying that you can basically dissect your model into several different sections, and essentially check your turn off the model that you don't want to train, and the rest of them are still trainable. And that's basically the point I'm trying to. JK, this is still not the actual example. Another freezing example here. Okay. So the next one, I think, get into the actual model. Yeah, and for neural network training, so there, so this is actually the transfer. So all the example that given above is not really related to transfer learning, although the freezing part is a little bit related to that, but it's not really transfer learning because we didn't input any data. We do not have back propagation, front propagation. We don't have anything. So I do only explain to you what is actually freeze. So now we're actually using a simple example. This example is classifying cat and dog. So this is actually an example of a transfer learning of a whole system, how you can use transfer learning to essentially complete a task, a binary classification of that cat and dog. And someone is, can we get model summary? Yeah, I could do that. Print, may do model dot summary. Cool. Now you can see the different models, sequential 20, and then still, and the 20 is essentially what's happening in the model. Thank you. That's actually really good. And it's classifying class task is classified. So for all neural network transfer learning, like for all of those deep learning examples, we must start from the very first step, which is importing the data set. So TensorFlow datasets as TensorFlow datasets. Okay, and now I'll just turn off the progress bar. And we'll define the training data sets, validation data set, test data sets, and etc. Right here. Does anyone has any questions regarding how to split the data sets? What is training data set? What is testing data set or validation data set? Everyone's clear? Cool. Okay, we will just go out validation data sets. Test data sets equals to TensorFlow data sets load. Here, the first parameter is supposed to be the data set name. Cats and dog. this is embedded into the TensorFlow library, so you could just directly reference. And essentially, we decided to use to make your shorts, just do string. We use what is a good number? Maybe 40%. We'll just use 40%. And yeah, still have to be. So I'll just do 40% to 50 as the handout suggested. And this is, whoops, accidentally typed it, 50 to 60. So now we're just saying that we're going to use 40% for the training data set, and the 40% to 50%, we're going to use it for validation purpose, and 50% to 60% is used for the testing data sets. And because we're doing supervised learning, because this is binary classification task, and we're only using, the exception model to start, so it is supervised learning. So we do need the labels, and then that should be it. Let's see if it first disable progress bar. Disable progress. I definitely misspelled GRESS, progress. Yeah. So it's downloading. This will take a while, so if you guys type it down, we'll just start on the next step. Actually, we'll just wait up for a little bit because I want to make sure the data loading correctly. We'll just wait for a little bit. Okay. And this is done. So we'll just print to make sure the number is correct. So we'll just do number of training samples. So we'll just do whoops, this is her reference in Python PDF data experiments. So cardinality. Yes. Cardinal. Yeah. I'll copy that whole line and testing the validation data sets. Yes. Test data sets. Okay, now we can see that because we're using 4 10 10, so this is approximately 4 times as much as this. Although like some of the images are corrupted, so it's not exactly time 4, but it's gonna be close, and maybe a little bit more than that. But it's this is kind of like the right proportion that we're looking at. If you think that training this on the accuracy still does not meet your requirement and you are looking to use more samples, you can increase the number here. So maybe you can use, I don't know, to 60, and this one could be 60, 70, 70 to 80 here. And now you can use a more reasonable split for you. But here I'm just using this to keep the consistencies. And the next step is that after we load it, we actually might want to see what is happening with our codes. And Matplotlib, pyplot. So this is a common library that's used in Python to visualize your data. I'm pretty sure you guys will use it when you want to plot something, maybe like train graph, scatter plot graph, or I don't know, histogram for some of your science report. This is actually really useful. And let's do PLT figure. So fixed size equals to 10, 10. So I'm using 10 graph to 10 big size. That's actually the size of the graph, I think. Where I image, because I want to include both the image and the label to make sure that they match up properly. So I'm just saying here, enumerate PST. And do X equals to. So I'm starting a subplot. And 3, 9 plus 1. And PLT. Show. Whoops. PLT. Title. So I'm essentially putting the label as the title for this plot. Turning off the axes, that's it's become more clear here. Whoops. So now you can see that I'm taking 9. So this exactly is this what's happening here. I'm using a 10 times 10 kind of figure size to plot the subplots. And then because if I increase this kind of will increase the plot right here. So I'm just setting it to 10, 10. And here take 9 is I'm taking 9 graph exactly from the training batch, which later your model will see. So this is data that your model will see. And if I just change this to test DS. This is essentially some of the graph from the testing data set. So I'm just visualizing what exactly your model will be seeing. And as you can see that if it is a dog, it will return 1. So that 1 is the true label for dog and 0 is the true label for cats. And because, you know, like, we could do something like, we're just putting the integer here, but we could also, you know, instead of doing this, we can just do if label is, if int label equal to 0, we can set, whoa, we'll accidentally type something. And about just a cat. Title, can't spell, dog. So now you can see that the cat is labeled as cat and dog is labeled as dog. So this is just a fast way to visualize your training data for you. And you should always be doing this in your own time, because this actually helped you to avoid some bad mistake. Like, you know, if you print all of your label out, or sometimes instead of doing this, you might want to see how many samples of cat are in your training set and how many dogs are in your training set, because sometimes you might see that your accuracy is incredibly low and you don't know why, because everything else seems correct. And that might be due to a biased, you know, training set that you have used, that you should have used approximately the same samples of each class in order to reach the balance. Anyway, but this is just a fast way to visualize it for you. And that's a really cute dog. I will just keep going. And I think, yeah, and now we're just gonna resize the data. So size equals to 150 to 150. So we want to print every single graph to the size of 150 and with 150, because later when you're passing the graph into your essentially model, you need a fixed size for that, because if you're using an 8 and you might want to flatten this, right? So you have 100. So if this is clearly a rectangle here, and the sizes and the scaling is different. So when you're passing to a neural network, it's computer programmed, so it has a fixed configuration and it does not accept, variant sizes of different images. So what we want to do here is that we want to fix the size to some square. Usually we're using squares, but sometimes we might want to use rectangle if that's what we want to do. And sometimes we even want to ditch the, like the RGB channels. We want to only take the grayscale of an image. That's also what you can do with it. But in this case, we're just gonna rescale this whole graph to 150 and 150. I mean pixels, 150 pixels by 150 pixels. And another thing that we might want to do is that we want to cap the color channel sizes. But I don't think we're doing it in this case, but might need to do it later. I'm just using lambda here, and because it's fast and does not need to redeclare yeah, size. Whoops. What? Sorry. Why? Messed up the bracket here. Cool. Does anyone need some clarification on the lambda, or are we all good? I think we're all good. Yeah. So I'm just changing the declaration name here. Test data sets. So now if we do this again, clipping data to a valid range of RGB data for floats for integers. That's okay, we'll just not plot it. The range. But although I know the graph kind of seems weird because let's see, TensorFlow image resize, because we're using essentially we already clip it to, I think it's -1 to 1. So here the data, the RGB value appears to be a little bit weird. I could essentially unclip it, but just look at this graph. I just want to show you that the size of these graphs are now square and they're the same. So that's the point. So by the operations right here, we're essentially clipping the each sample of the train DS and validation DS and has DS to the size of 150 and 150. And here I think map is its lambda value. Yes. Let's see. For MShow with RGB data for floats and for integers. Yeah, I think the input data got a little bit weird by the resize operations, but the shape is the important part, which is visible from this case. So now let's after we have the training sets, next step is that we're gonna put all training data into batches, because we want to use maybe stochastic gradient descent, maybe mini batch training. So here we need to basically essentially divide the whole data set into small batches and train. And sometimes maybe your GPU cannot handle that. You might want okay. You might want to divide it into larger or bigger sizes. Larger or smaller sizes, but it's all dependent on your case. So it's your personal choice. You can play around with these values to essentially to change your hyperparameter of your model and enable your training to go faster, slower, more precise, or whatever you want. So yes, cache batch. Whoops. Batch size. Come on, yeah. Prefetch. It's 10. So don't be intimidated by the cache prefetch here. This is just some sort of trick in Keras to enable you to train faster. So it's just essentially using a cache to store some values in so that the fetching time will be smaller. That's the brief explanation here, validation. Okay. We will just copy and paste this. So SDS. I apologize for the slow typing today because I am using my computer. Yeah, I'm using my computer keyboard, and it's not my favorite things to work with. And run this. Now we have divided into by the training set into a small batch of 32, 32, and 32. And just maybe add a bit here. So this is the cache as well as the prefetch buffer is to optimize the loading speed. Cool. Next step. Run this again. Cool. So because we only have a few thousands of training samples, 9,000. Usually this is enough for like an 85% just binary classification task. But in this case, I think I will just include the data argumentation. That means that we're gonna some sort of process the given image. Like we may want to rotate, we may want to flip it, we may want to, I don't know, change the color scale of it to make it to although they're the same diagram, okay, but after the data augmentation, it may look different to the machines such that we have more data to train with, and perhaps that will help our machine to learn better about the different property of our data set as well. So this is just the data augmentation part. Keras. Okay. Sorry. Keras. Imports.
Sorry, I have a question.
Yes.
There was a time that for data augmentation, you used albumentations, I guess, if I'm not wrong, the framework.
Sorry?
The albummentation framework for data augmentation.
Can you maybe like spell it in the chat so I can look at it?
Sure.
Maybe I just misspelled it. Augmentation. Maybe this. Augmentation. Sorry, I think. I'm actually not familiar with this vocabulary. I think it may be some sort of misspell of argumentation, but for in the same context though, if it refers to the same thing, this data augmentation means that we're altering the data structure. Yeah, we're essentially altering the structures of the image without essentially changing the nature of it. Actually, we're changing the image, but we're not, like meshing it with some other photos or stuff. The photo is still the same photo, but we're kind of like rotating or adding more, image color to it or stripping colors to it to make a new image that seems to the models. And because I'm not too sure what this vocabulary refers to, I'm just explaining this case that data augmentation means that. And later I'll do some research into it and make sure if they refers to the same thing, then that's all good. If they refers to different things, then I get to learn. So yeah. Yeah, thank you for asking that.
No problem. Thank you, though.
I'll just create argumentation. Arg, yeah. And that's sequential. So I'm using this sequentially again, but in this case, not in the model context, because in this case, I'm just kind of concatenating different layers operations such that I can just pre-process the image before the training. Horizontal, whoops, this is definitely not horizontal. Yeah, layers, random, rotation, 0 to 0.1. That is because I'm missing comment here. Layers, layer. Yeah. Maybe it is layers. Yeah, it's layers. Oops, sorry. Yeah, and now this works. If let's just visualize it a little bit. Sure. So now after data augmentation, let's just visualize it for a little bit. NumPy. Labels, yeah, sure. In train vs. I will only take one photo. First. I'm grabbing the first image here. What's happening? Okay. Whoops. Images. Yeah, images. Sorry, the first batch from the images. And argument images. What did I name it here? Argument image data aug. Yeah, so I'm actually augmenting them here, and that is TF. Oops. TF dot expand. Yes. First image. Sorry, in this case, I'm naming it first. This is training. Was true. Image show. Display argument. Zero. NumPy. So that's correcting essentially the mistake that we're seeing like above, because before we have the clipping input data error, and now we're just fixing it right here. Let's type in 32. Yeah. Whoops. Title. Labels. Yeah. Here. Great. Okay. Let's see what's wrong with it. Extending first equals to, what's this error? Exception countered when calling layer random flip. Horizontal. Here's control. Image, train gas take 1. Fixed size equals 1010. Should be fine for this line. Images 1, I'm taking only the first image for I range 9. To subplot 3x I plus 1. That's also correct. Data augmentation. Data aug, I name it here. And TF first 0 and change to NumPy as type. Or image labels to take 1. So it's still this line. Or received by layer. 132, 150, 153. Training equals 3. Okay. Right, spending to rank 3 for G tensor Gauss shape. Okay, so the shape is not correct. Let me just rerun everything up until here and we run everything up until here. I think it's some back and forth issue. And now it works. It's because previously I think I go back and forth somewhere for here, and I essentially ruined it up for the reading parts. But now when I rerun it, that should work. Okay. So I just want to show you how data augmentation kind of work. Is just taking the same image and I'm just clipping first and randomly flipping. As you can see, this one. Whoa, okay. This one and this one is kind of just flipped. And then rotate 0.1 is that remaining same image sizes. I'm just like rotating it for 0.1. I think it's, I don't know, I'm not sure about the unit in this case, but 0.1 is kind of just maybe like 0.15. I don't know, some sort of degree measurements that, as you can see, that this one is kind of just randomly rotated between a scale of 0 to 0.1. And then this is flipped. As you can see, this is more rotated than this one, but the image sizes still remain square and yeah. So next step, we're actually reaching to the transfer learning part, and actually we're almost done. So just stay with me for a little bit more. So next step is that we're gonna define a base model. Exception. I'll go through what exactly is inception and maybe exception in this case. This is just a Keras embedded architecture. It's not really famous, but this is what the tutorial used. You can also use VGG. They also have VGG, but exception, one of the really good advantage of exception is that it's fast because its layers, architecture actually use separable layers instead of just normal CNN layers. And by remaining the inception kind of structures, but with the separable layer, it has much less parameter to train, and thus it's enable a fast training speed. And I think that's why the tutorial is using it, but this is not a really famous or traditional structures. So if you guys want to try with it, you can also try VGG, maybe like LNet something. So the other one works a little bit better, but So we're just using it in this case. So we're loading the weights. And also this is pre-trained weights for Keras based on the ImageNet. So in ImageNet, if you guys are curious, it's a very well-known essentially database for okay. Home. That's a challenge. Yeah, for neural network image retrieval. So you can download different type of, you can download different type of image here. And for your own, if you're just developing a neural network from scratch or stuff, you can get the data sets on its website. And all of these data are also from ImageNet as well. And this model for Keras, their application is trained on this ImageNet data as well. So we're just keeping the consistency here. It's 150, 153. Okay. Last step is include top. Include top. Just false. False. Okay. So here we're just not including. So here we are not including the ImageNet classifier. It's not good work. Oh, I forgot to comment here. Whoops. Application. Okay, so now you can see that it's downloading data from if you go to this link, it's essentially what Google APIs. This is Google Colab, and it's storing TensorFlow. This is TensorFlow's library address for Google Colab, and it's an API, and it goes to Keras application, and it goes to folder of exception, and they have the exception weights for TensorFlow, and yeah, and no top because we're not including the ImageNet classifier at the top, and yeah, that's our base model. So that means that this is the model. This is the weights that we're gonna freeze at the first step. So because we want to freeze it at first because it's the starting point, and we don't want to ruin it, as the slide that I just showed at the very beginning of the class. Yes. So now we're just turning off base model, trainable. This is false. Cool. And we need to build new model on the top. So here's a question for you guys. What do you think is the input shape for our new model? Actually, maybe I'll just do this first because I think that's pretty weird to ask. Oh, inputs. It could varies depending on what I'm doing next. So I'm just gonna because I haven't done the data augmentation first. Sorry. So it could vary because right now our data is still like not augmented, although it's processed. So I gotta do this first. And inputs. I think I name it yes. And the next step is scale. I need to scale it from RGB, which is 0 to 255, to range of -1 and 1. Yeah. Sorry for the stupid questions that I just put out, because that was way too early to ask that. And right now I'm just trying to, so the original range for the RGB is 0 to 255. So now what should I do if I want to change this to this? Is that for the next step, I'm gonna do scale layer plus dot layers dot rescale. Scale equals to 1 divided by and the offset equals -1. So here's a hint here. So the output is, the output equals to, whoops, sorry, scale plus offset. So this is how I transform from the RGB to the range of -1 to 1, because this is the range of the weights that I take for the exception block. So we have to transform beforehand to enable the performance of our model. So how exactly for me to do that is that originally I have 255 for our RGB value, and it divided by 2 and kind of inverse it, and I offset it by -1. So for example, if we originally have 255, because of originally from 0 to 255, whoops, and I want to transform it to the -1 and 1 scale. Can somebody tell me what is the expected value for after the transformation? Like a 1, right? Because it was originally from, it's linear transformation, by the way. So it was originally 255, and after that we want to change this range essentially to this range. That means that we need to shift and squeeze. So how I do that is that I kind of squeeze it first. So originally this range has essentially a magnitude of 2, right? And this range has a magnitude of 255. That means that for the 255 magnitude to be squeezed into 2, I need to divide, essentially time this scale. Sorry, I essentially need to time this range by a scale of 1 over 255 divided by 2. And that kind of squeeze the magnitude of 0 to 255 to 2. But the next step is that I still need to offset it, because the lower bound is different. Originally it started at 0 and now it started at -1. So I start another offset. So I divide 1 in this case, so that now all of the photos are ranging from -1 and 1. Okay, hopefully that makes a little bit more sense. And because I named the, now I'm just gonna scale it for the X.
Sorry, just a question. The scale layer variable, would it be changing from -1 to 1, or it just stays a constant?
Sorry, pardon?
The scale layer variable, does it change or it just remains constant?
The scale of the
The scale
variable?
layer variable, so it changes from -1 to 1?
-1 to 1. So what do you mean changing from -1 to 1? So we're not changing anything here. We're essentially mapping the originally a graph that you might see maybe have like 4 pixels, and the 4 pixel might be like 255, I don't know, 100 and 0 and stuff. But now we're trying to map it to another, I guess, another scale, because originally it was 255, 100, 0 to 0. We want to remain its like a numerical relationship, like this is the upper bound of its RGB scale, and this is the lower bound of the RGB scale. And we want to remain this numerical relationship, but because the exception block, the exception model architecture that we're using for the transfer learning only take image which has an input range of -1 and 1. So now we're trying to transform this to something like 1. Well, sorry, I typed 0. And this is 100 divided by 127.5 -1.
Okay, got it.
Yeah, and this is -1 and -1. Hopefully this makes a little bit more sense. So this originally has 4 values, and after transformation it still has 4 values, but its essentially numerical scale is changed because we
Right.
want to match to the transfer layer. So
Okay. Yep.
hopefully that makes a little bit more sense. So
Yes. Yes. Thank you.
cool, perfect. Thanks for asking. And this line is for you to scale this layer, and I just scaled it. I'll just cool. And the next step is that I'm gonna start a little bit with the base model. So x equals to base model. So I'm gonna put in x and training equals to false. So now we actually see the training equals to false. Now, because we want to turn off the training such that our transferred weights, so right here, base model. Sorry, not there. Yes, there. So so the weights from our base model is all freeze at this point, such that later when we append layers to our transfer layer, the weights specifically will not change. So now we're just freezing it right here. And the next step is x equals to layers global average. We're using average pooling 2D because 2D photos, and oops, we're taking x as in heroes, layers, and we're adding dropout to regularize our, because this is still the weight that we're taking from oops, I'm always using brackets today. Because we're always taking the weights from the transfer layer, but that is specified for another task. So here we're trying to regularize its weight by adding dropout. So we're disconnecting some neurons to some neurons. So that's the task. Maybe before it's too specific, and by adding the dropout, now our training could become a little bit more easier. And this is also an average pooling to make the the original weight to be more regularized. These are all regularized regularization methods. Next step is outputs, layers dense model, implicit layers model. Takes 3 inputs and outputs. Cool. So now we essentially adding one more layer to the transfer. This is a really basic transfer model, because we're essentially just taking a whole block of pre-trained weights, which definitely is sufficient to do the classification of cat and dog. This is essentially a really easy binary classification task. So this is our transfer weight, it's called T. And we're only appending one extra layer that has, and it has one input. I think it has one output. Yeah, and it only produced one output. We're only appending this. So this is by us, and all the work previous done is by the ImageNet and exception training from the Keras library. And so here we're only producing one output, which is either 0 or 1 after, you know, whatever the maybe you want to use softmax and stuff to kind of just figure out the exact binary classification. There will be a, I think it will be a logic between 0 and 1. Yeah, in this case for here. And we're only appending one another dense layer after this to enable training. Anyway, there are lines. So I just kind of want you guys to know what's happening here. We have the input and the output layers. Here, now we have the model. But remember that only the outputs is trainable because we have turned the base model, essentially the inputs down. And here, let's continue. So, yeah, and let's just use this method to see that. Okay. So now we can see that we only add the last dense layer, and all the others, as you can see, we have so many parameters, but only the last 2049 parameters are trainable. Can anybody maybe take a guess why the number is 2049? Why the number is that? A potential tip is maybe here. Does anyone want to take a guess why this number is 2049? Why there's 2049 trainable? Sorry? Yeah, it's just 2048 plus 1. It's really, don't overthink it. Because this 2048 coming out from the exception is essentially the connection that we're allowed to have because we only have yeah, and the last one parameter, which is the input size for, you know, the output layer, and we're connecting after dropout, we have 248 trainable neurons. Yeah, trainable neurons, and we're connecting those to this one to make it a total of 2049 parameters. So it's totally not difficult. If you just match the numbers, this really should be fine. And then the next step is we need to train it. So the training process is just added. So training. We are so close to be done. Training. Whoa. Okay, so first we'll do a model compile. Optimizer, we'll use Atom. Here is optimizer. Optimizers. So as you can see, it has a lot. We can use stochastic. Some common ones are stochastic gradient descent, but Atom has kind of like embedded momentum parameters, and sometimes that's better. We'll just use it in this case, but there's cross entropy. Yes. BCE, we're using BCE. And from logics. We're just configuring the optimizer, the loss, and the metrics in this case. Here's metrics. As you can see, it's all defined for you. You don't get this if you're using PyTorch or DIY TensorFlow, because in that case, you kind of need to start from the I'm missing a black bracket somewhere. Is it here? No, that's not it. Where's, oh. I'm having one more rise here. Now it's good. Okay. Now I have the optimizer loss metrics now. So these are really good because these are all defined for you, but if you're in PyTorch, you need to kind of DIY using NumPy and also PyTorch to complete all of these, which is good. We have Keras. And epoch, we will just run one epoch in this case because I just kind of want you guys to get a feel of it. But usually you probably need to use more than one. That means that my model only has seen all the data once, and usually you want to let your model see the data a couple of times. Sometimes that's not good because likely if I only run one epoch, this model will be really underfitted. So, but if you let your model see your data for too many times, that will be overfitted. So we still need to see the learning training and kind of decide from there. But here I'm kind of just we're in a time crunch, so I'm just letting it see all the data once because we're dividing into batches and the model will update at the end of each batches. So that's we're still updating the model. It will just not be that good. And train, yes. When you have time, maybe train more and yeah. Equals to epochs. Validation data. Just the validation DS. Did I miss anything? Validation DS. Validate TION. Epochs. Epochs. And yeah, this is gonna take a while. So I am actually going back to change this. Well, I actually shouldn't be, but I want to speed it up. So I just use 35%. So I'm only using 5% of the training data, which is really bad. Don't do that. And yeah, this will take about actually I think it's training okay. I think it will take us several minutes to train. Because we still have 9 how many graph we have training data? I forgot. I think about 9,000. Yeah, we still have 9,000 to go through for our parameter, and our model has a total of this much parameter. So although you're only updating this much, you still need to perform a pass through all of these parameters. So it's still a relatively large models. Usually we won't have that much layer to complete a binary classification. Usually I think maybe 2-3 layers of CNN adding maybe a max pole while having a fully connected layer will be enough for this test for sure. But and which means that we're training up that one epoch kind of take maybe like 1 minute. But because this is a large model, without changing the training data previously, I really should because it's taking a while. But without changing it, this will take approximately maybe like 3 minutes to train. And also, I'm not sure if it is using GPU. I don't think it is using GPU as well. So Google Colab has GPU, but we're not using it. So, sorry. I haven't write the code for that. Yeah, I think I need to configure the device, like Cuba devices and stuff. And I don't need to. It does use the GPU. I think go to runtime. Okay. Here. Let's actually try here, which is good. We're getting yeah, I need to Okay. But also I would need to change this back to 40 because I think if we have GPU, this is much better. Where do I have maybe like 40%? Yeah. 40% train. Just take this off. Whoops. I would need to rerun everything I have to. Yeah. Cool. Thank you for that advice. I totally do not know Keras just configured GPU for you. I totally don't know that because I usually don't use Keras, and yeah, I usually use PyTorch, and I have to configure the Cuba for myself whenever I want to use it or not. So I'm actually amazed. Cool. Thank you so much. It's awesome. It's faster. Oh, thank you. So I just yeah, it's much faster. Perfect. Let me say, someone is asking a question. I got this error input 0 from others. That was expected non-53. Bound shape. Or model. While trying to do model fit. That means that I think maybe your input layer is configured wrong because your input layer right now is 150 and 150 and 3, and your expected value should have one more parameter. That means that your input is some sort of off. But whoa, that is much faster. Thank you. That's really good. And I'll post this handout after the session so that everyone could rerun the code and see where is the difference between your code and my code, and maybe that will help you a little bit when debugging the parameter. Always parameter matching is a bit of a pain, I understand. And right now the accuracy is at around 92. If that trains really fast, and I just finished 5, which is good. Thank you. It's pretty fast. Okay, cool. And by bringing it, getting it, we're almost done. Well, that's perfect. That's super fast. Trainable, true. Optimizer, Keras, license. Wow, that was super fast. I was training yesterday for like 20 minutes. I was like, I was definitely not gonna do that in class, but like, cool. That's awesome. Sorry. Let's see. Yeah. So here, after this, while we're just waiting it to be done, the next step of our training, as the slides that I showed at the very beginning of the class suggests, that we need to unfreeze the base model. So essentially, we need to release our beginning point and allow that part to be trained as well. And after we have like really good after layers, so that this model now can be fully adapted to the task that we're looking at. And now we'll just run it for, because we have much parameters to train, maybe like 2. I think this will train much slower than the previous one because we have more trainable parameters. Pause 2. Pause. Yes. validation data. Yeah, because it's running the previous pairs, it's not giving me any pop-up, so I might have a lot of wrong typing here. Yeah, let's see. So this is kind of improving, but not really. But it's definitely not overfitted because this accuracy is less than that, and definitely the validation is better than the training loss. So I'm just gonna. Sorry, I lost it. Training. How is training loss? What? How is training loss higher than validation loss? Just because we have a smaller, yes, just because of a smaller batch of validation data, I think in this case. It's because the originally exception weights that we're taking is already good enough for this test, to be honest. So there shouldn't, like, the training shouldn't actually improve the accuracy, but it's really rare for the first epoch we already have a 95 accuracy. That's just we have a really good architecture right here, and we have a lot less just validation data right here. So the accuracy might be also a little bit higher, as well as the loss. So this is not actually, it just suggests that just from the number, you might seem, okay, this is underfitted. But like, this is first epoch. So I think this kind of makes sense. So I think I mistyped something. Optimizers. Here we go. No? Okay. Model. I don't have any auto summaries. What's the validation? Of course, I misspelled it. Validation. Okay, cool. Yeah, as expected in this case, it's definitely training. Actually, not too bad, but it's a little bit slower than previously because we have more parameter to look at. That turn true? Yeah, I do. Yeah, this is gonna take a while, but essentially after this step, we're done with the training of the transfer learning example, and this is the all of the content I have for today. But let's just wait until to be finished and look at the accuracy. Although I don't think the accuracy will have a substantially increase just because 96 is already 95, 96 is already a really, really good number. And I don't think the last 2000 parameter could do such a huge impact on the previously transfer learning data just because the exception architecture is already good enough for this task. Like the pre-train weight is already pretty well done for this task. Let's wait a little bit more. Okay, come on. Okay, that's the first epoch. And we're at a 96, 97 accuracy. So after we trained everything, so we're updating essentially now we're updating the exception weights to our own weights to kind of follow this specific task, to back propagate it into some sort of weights that's more fitted for the classification of the cat and dog. And now we have a binary accuracy of 97%, which is awesome. That's actually really high. And it's still updating, but we're almost done for the second epoch. Usually, I usually, for when I'm training for epoch, I usually do maybe like 20, 30. 2 is definitely too little, but in this case, because I already have a really, really good beginning point and task is too simplified, to epoch, you're already at 95. But so normally, if you start from scratches, at your first epoch, this number will around 50, a little bit about, or 60. Sometimes you train for 10 epoch, and the accuracy does not have even a little bit of change. So we're almost done. So just wait for a little bit. Wow, the accuracy is actually really high. I'm curious about the validation. So it's even higher. Cool. So it's now it's calculating validation. 98. Cool. And now we end at about 97.5 binary accuracy. Because I don't have a fixed random seed for this example, your trial result might be different from mine. That doesn't matter. It should land at the same magnitude as this. Anyway, yeah, that's it. Do you have any questions regarding the whole content, or is there any extra content that you want to know about? Meanwhile, sorry, I'm just gonna share the link. So anyone with link can view. I need to copy it. Yeah. This link will also be posted later on the website. I believe Mindy, our lovely TA Mindy, will help us to do that. Thanks for